We are discussing laws of motion. In the previous discussions, we have talked about the motion of a particle in a space, and that too we talked it in the quantitative basis. Then we talked about the concept of velocity and non-uniform motion, and then we talked about the acceleration. But one question we didn't ask, that what is governing the motion of bodies? In this discussion, we are going to discuss this only. Let us see what our experience says. When the football is at rest, why is it at rest? When someone kicks it, why does it move? When we throw a stone upwards, what is the thrust or force or push you give so that it reaches upward? A breeze may cause the tree to swing, and even the strong wind can move heavy objects. The boat which is moving in the river, if you're rowing it. So there is some external agency in all these scenarios that is providing some force. So there is some or the other force which is making this body to move. This external force is also required to stop something. Means this ball which somebody has kicked, football, then you can just stop it and it will come into, you can say, rest. The external agency of force in all these scenarios, it can be your hand, it can be wind, it can be stream, and these are all in the contact with the object, but this is not necessary. Take a scenario, you are dropping a stone from, say, a building. Now there is a gravitational pull here. So this is not having any contact with anyone or any other agency, but it is having a contact or some kind of pull with earth. A bar magnet can attract iron nail from a distance. So what this shows is that the external agencies, gravitational it can be magnetic forces, this also exert force on a body, and that is at a distance. See, it can be, say, 100 meter, 200 meter. So the force is required to put a stationary body either in motion or to stop it, means to stop it. And there must be some external agency which is providing this force, and as discussed here, the external agency may or may not be in contact with the body. But what happens if a moving body which is moving uniformly, that is, say, a skater, he is moving with a constant speed on a horizontal ice slab? Do we require any external force to keep a body in this uniform motion? We have Aristotle fallacy. Now Aristotle gave his ideas, his view. And why this is called fallacy? Because there is some flaw in his argument. The question about what is the force or how the motion of the body is governed, it was somewhat discussed by Aristotle, and then Galileo came in the 17th century and he gave you can say the flaws he cleared, and then Newton came, which gave rise to Newtonian mechanics. Basically, what Galileo has thought, or what he has posed in front of us in the 17th century, this is the foundation of Newtonian mechanics. So what happened? Aristotle, he was a great thinker. He thought that if a body is moving, something external is required to keep it moving. He gave certain reasons also. he said that arrow shot from a bow, it keeps flying since the air behind the arrow keeps pushing it. And people that time, they might have believed, and most of his ideas, Aristotelian ideas on motion, they are proven wrong today. But because he started, we need to understand what he said. The Aristotle law is like this: an external force is required to keep a body in a motion. And what is the flaw? Anyone of common experience or common intellect will go with what Aristotle has said. Even a small child who is playing with simple, say, non-electronic toy car on a floor, he knows that he has to either pull it or push it, say, constantly drag this string toy car with certain force in order to keep it going. Now, if he has a string and he releases the string, it will come to rest. This is common to all terrestrial motion also. We understand that there are certain external forces. This seems to be needed to keep bodies in motion. And all bodies, they eventually come to rest. So what is the flaw? See, the moving toy car come to rest because of the external force of friction on the car by the floor, which is opposing its motion. So in order to counter this force, the boy or the child has to apply certain external force on the car in the direction of motion. When the car is in uniform motion, there is no external force acting on it. The force which child has exerted, or he has pushed, the friction force and this force will get cancelled out. So if there were no friction, the child would not require to apply any force to keep the toy car in uniform motion. So we have opposing force like friction in solid, viscous force in liquids or fluids that are present in natural world. And that is why we know that external forces are required to overcome this frictional force in order to have a uniform motion. So this is the Aristotle fallacy. He coded this practical experience in the form of just basic argument. And if you want really to have forces and motion and the nature and the laws, then we have to imagine a world in which uniform motion is possible with no friction force opposing. And this is what Galileo did. The law of inertia. Galileo, he studied the motion of the objects in the inclined plane. He saw that the ball which is moving up, which is coming down, or which is in the horizontal position, these all scenarios he took. And he finally concluded that an object moving on a frictionless horizontal plane must neither have an acceleration nor retardation. Acceleration means increasing the speed, retardation means decreasing the speed. So when it has no acceleration, that means it is moving with a constant velocity. There is another experiment which Galileo did, and this also strengthened the idea which he discussed here. And this was double inclined plane. So a ball was released from the rest on one of the planes, rolling down, and climbs up here. If the planes are smooth, the initial height and final height, they are nearly same. So what is the ideal situation? When friction is absent, the final height has to be equal to the initial height. Now, if the slope of this second plane is decreased, and again this experiment is repeated, it is done again, the ball is going to reach at the same height, but It has to travel a longer distance here. And in the limiting case, the slope of this second plane is made 0. The ball would travel an infinite distance if it is dropped from here. Or you can say the motion will never stop. But we know this will not happen. This is not an idealized situation. In ideal situation, it should not stop. So this is the experiment, these two experiments. The law of inertia was inferred by Galileo from these observation of motion of a ball on especially these double inclined plane. We see that ball always come to a rest after some time because there is opposing force, which is friction. We cannot totally eliminate it. It will be there. But you will see that with no friction, the ball would continue to move with a constant velocity on a horizontal plane, if in case friction would not be there. So Galileo now arrived at new insight on motion that had eluded Aristotle and those who believed in Aristotle. The state of rest and the state of uniform linear motion, that is motion with the constant velocity, they are equivalent. Again, the state of rest means if the body is settled down, not moving anywhere, and the state of linear motion, if it is moving like this, they are equivalent because there is no net force acting on it. Net force means a body may be subjected to certain force like this one, this one, this one, and the final force we have to find out. So that is the net force. So it would be incorrect to assume that net force is needed to keep a body in uniform motion. In order to maintain a body in uniform motion, we need to apply an external force, and that is to encounter, you can say, counter the frictional force. So these two forces sum up to 0 net external force. So let us summarize. If the net external force, that is this one, is 0, the body at rest continues to remain at rest, and a body which is in motion will continue to move with a uniform velocity. And this property of body is known as inertia. This is known as inertia. Inertia is simply meaning any resistance or the resistance to any change. That means the body does not change its state of rest like this or uniform motion unless it is compelled to do so or some external force is applied to change that state. Newton's first law of motion. Galileo, the ideas he gave, actually Aristotle started all, and then Galileo gave the flaw in Aristotle and he corrected the concept. After that, new mechanics was developed, and this was accomplished single-handedly by Isaac Newton, one of the greatest scientists of all times. Newton started, or he took Galileo's ideas as the base, and then he laid the foundation of mechanics in terms of 3 laws, which we know by his name. So Galileo's law of inertia was the starting point, which was he formulated in terms of first law of motion. Every body continued to be in the state of rest in a straight line or uniform motion in a straight line unless it is compelled by some other or external force not to do so. So the state of rest or uniform linear motion, they both imply 0 acceleration. Acceleration is 0 while the body is at rest or in uniform velocity. How can we express it again? If the net external force on a body is 0, its acceleration has to be 0. We'll see later that in the second law of motion, F is equal to ma. We'll learn about this. So F equal to m into a. If the acceleration is 0, force is 0. So acceleration can be non-zero only if there is a net external force on the body, right? This can only be non-zero when you have some force here. The net external force in the body, if it is 0, as we said, because of this discussion, the body is either at rest or it is moving in uniform motion. A spaceship out in interstellar space, which is far from all other objects and with all its rockets turned off, it has no net external force acting on it, that is zero force acting on it. So the acceleration, according to the first law, it has to be 0. If it is in motion, it has to move with uniform velocity. So where does this force comes? That the object is, say, accelerated or unaccelerated. You can say if it is unaccelerated, that means it is in rest or uniform linear motion. What we can infer is that by first law, that the net external force on an object must be 0. But gravity is everywhere. If you take any terrestrial phenomena, every object experiences some gravitational force which is due to the earth. The objects in motion, they generally experience the friction, the viscous drag, so many things. So the net force which is acting is very important. We'll learn about that, how those forces cancel up, how those forces they get added up. Just consider a book which is lying on the table. Now there is a force of gravitation which is acting downward, which is W, weight. There is a normal force opposite to it, and this R is self-adjusting force. These forces are opposite to each other. That is why, what is happening? This book is at rest. So what we can conclude by the first law, that the magnitude of R has to be equal to W, because this is at rest. So all the net force which is acting on this body should be 0. So there is only two forces which we can conceive here. One is weight, one is some reaction force. So R has to be equal to W, and they cancels out. And since they cancel out, the body remains at rest. But is this reasoning correct? The correct discussion should be, since the book is observed to be at rest, there is no net external force on it, or the net external force on it must be 0. So R minus W equal to 0. This should be the proper reasoning. That means the force, this R, has to be equal and opposite to this weight. Let us take one more example, that is a motion of a car which is starting from rest. It is starting with initial velocity 0. That is picking up speed and then moving on a straight road, and now it has uniform speed. When the car was at rest, that is, it was stationary, there was no net force, but during pickup, you push the acceleration is being pushed by you. Okay, and there would be some external force. That is why it has accelerated, and there is no external force here because the acceleration is coming from the engine. So the acceleration of the car cannot be accounted for by any internal force. But it is true. It is surprising, but it is true. We need to understand only the conceivable external force along the road is the friction force which is acting between the tires and the road. This is the friction force which is being acted upon. So when the car is moving with constant velocity, there will be no net external force. And the inertia, body will continue in rest, body will continue in moving state. When we are standing stationary in the, say, stationary bus, and the driver starts the bus suddenly, what will happen? We will get thrown backward with a jerk. Why? Because our feet, see, we are sitting like this. Our feet are in touch with the floor. So if there were no friction, we would remain where we are, while the floor of the bus would simply slip forward under our feet, and the back of the bus would hit us. But what happens? Fortunately, there is some friction between our feet and the floor. So if the start is very fast, if it is not too sudden, you can say the acceleration is moderate. The friction force would be enough to accelerate our feet along this bus. But our body is not a rigid body, it's flexible, it is deformable. So it allows some relative displacement between different parts. We can move our parts. So which means that while our feet go with the bus, the rest of the body remain where it is due to inertia. So relative to the bus, therefore we are thrown backward, and as soon as this happens, our muscular force, body forces, they start acting upon, and they play to move the body along the bus. And this same scenario will happen when the bus will suddenly stop. If it suddenly stops, our feet stop due to the friction, which does not allow relative motion between the feet and the floor of the bus. But the rest of the body continues to move forward due to inertia. That is why we are thrown forward. But we have restoring muscle forces. This will come into play and bring our body to rest. Let us take a question. An astronaut accidentally gets separated out of his small spaceship accelerating in interstellar space at a constant rate of 100 meters per second square. What is the acceleration of the astronaut the instant after he is outside the spaceship? We have presumed that there are no nearby stars that are going to exert gravitational forces on him. And since it is being said that there are no nearby stars to exert gravitational force on him, and this small spaceship exerts very little or negligible gravitational force or pull, the net force acting on the astronaut when he comes out of the spaceship is zero. And we know by the first law of motion, the acceleration has to be zero. Newton's second law of motion. The first law of motion, it deals with the external force, that is no external force on a body. If there is no external force on a body, or the external force on the body is zero, then the body will remain at rest, or it will remain in uniform motion, uniform velocity. The second law of motion, it refers to general situation when there is net external force acting on the body. That is, it is relating the net external force to the acceleration of the body. Momentum. What is momentum? P, represented by P of a body. This is simply defined as the product of mass and velocity. So P will be equal to mass into velocity. Momentum is clearly a vector quantity because velocity is a vector quantity. We have certain experiences that will indicate the importance of quantity for considering the effect of force on motion. if we have a lightweight vehicle and a heavyweight vehicle which is parked on the road, now which of the body would need greater force to move? See, and even to move, to start, and to stop. In both the cases, which body will require more work, you can say. Heavy body, we need to work a lot with heavy body, and even to stop it, we need to work very hard. If two stones, one is light and other is heavy, they are dropped from the same height from a building, say they are two stones like this, and which one is easier to catch and which is going to affect, so if you are catching, then which is going to hurt you more? Speed is also a very important parameter when we consider all this. Speed, when the bullet is fired by the gun and it pierces human tissues, it causes casualty. But if the same bullet is fired with some, say, moderate speed, it may not cause that much damage. So for a given mass, if the speed is greater, the opposing force which is required to stop this body will be larger. So if we take mass and velocity, the product of mass and velocity, we know by now that it is called as momentum. And this is a very relevant thing which comes into play in terms of motion. So greater the change in the momentum for a given time, greater is the force applied. See how this momentum is related to the force. Just take an example. A seasoned cricketer will not just catch ball right here. He will catch the ball and he will take it backward. Why? Because there is a momentum, there is a mass in this body, and with a velocity it comes. So the rate of change of momentum, he wants to make it less. So force not only depends on the change in the momentum, but also how fast the change is brought about it. As we see here, the seasoned cricketer, he draws in his hands during a catch, and he pull it backward, allowing greater time for the ball to stop, and that is why he requires smaller force. So the rate of change of momentum becomes a very important property here, or you can say momentum becomes a very important property as far as force is concerned. So mass and velocity, as we said, is momentum. This is the basic to the effect of force on motion. If we have fixed force which is applied for a certain interval of time on two bodies of different mass which are initially at rest, the lighter body will pick up a greater speed than the heavier body. But at the end of the time interval, the observation will show that each body acquires the same momentum. So what this says is, the same force for the same time, causes the same change in momentum for different bodies. And this is very crucial when we are discussing the second law of motion. So in all these observations, because momentum has velocity, the vector character or vector property comes into play. The momentum and change in momentum, they both have same direction. But this is not always the case. Say you have a string and you have a stone at an end of the string, and then you are moving it. Now here the direction will change. So the force is needed to cause this change in momentum vector. See, the force is provided by our hand through the string, and this experience will suggest that our hand need to exert a greater force if the stone is rotated at a greater speed or in a circle, so say it's in a smaller circle. So this corresponds to greater acceleration, give rise to greater acceleration, or you can say the rate of change of momentum vector. This is suggesting that greater the rate of change of momentum vector, the greater is the force applied. So force is somewhere directly connected to the rate of change of momentum. So these qualitative observations lead us to the second law of motion, and which is expressed by Newton like this. The rate of change of momentum of a body is directly proportional to the applied force, and this takes place in the direction in which the force is acting. Say you have a force F, this is acting for delta t time. So the velocity of a body, say of mass m, it changes from v to delta v. In delta t time, the velocity change is delta v. So what will be the initial momentum? It will be simply p equal to mv. What will be the final momentum? Delta p will be equal to m delta v. And according to the second law, the force is directly proportional to the rate of change of momentum. So F is directly proportional to rate of change of momentum. So this is proportionality. Let us remove this, put a k here. So this k is the constant of proportionality. When we take the delta t, that is delta t limit tends to 0, when the time is very less, we make it, this delta p by delta t will eventually become the derivative or differential coefficient of p, which we represent by dp by dt. So now this f becomes k into dp by dt, and we know that dp by dt, p is what? M into v. Let us put p equal to mv here. Mass is constant, so take it out. This dv by dt is what? This is acceleration. So finally, F becomes k into m into a. This shows that the force is proportional to the product of mass and acceleration. This is the law which we are discussing. So the unit of force, what will just take a liberty that this k will choose as 1. So F is equal to ma. Now mass and velocity or acceleration. So the SI unit of force is 1, that will cause an acceleration of 1 meter per second square in a body of mass which is 1 kg. This unit of force is known as Newton. 1 Newton equal to 1 kg meter per second square. So there are certain points. If F equal to ma, F equal to 0 implies acceleration equal to 0. This is obviously consistent with the first law. If there is no acceleration, body will be at rest or body will be in constant velocity. The second law of motion, this is a vector law. So it is equivalent to the 3 equation in fx direction, fy means ax, x direction, y direction and z direction. So fx will be dpx by dt, that is max. Fy will be dpy by dt in y direction. So it will be may, and this will be dpz by dt for fz. This will be m into az. So this means that if a force is not parallel to a velocity of the body, this velocity is like this, force is somewhere like this, then it will make certain angle, and the component we have to see. We have to take the component, this component of velocity, which is horizontal, will be in the direction of motion, but the vertical will not change. We'll talk about the projectile motion, where we see that what is changing is the horizontal component only changes, vertical will remain like that. And this second law of motion is applicable to single point particle. The F and A, the law of motion applies to rigid body, or you can say a system, a whole system. This F, it refers when to total external force on the body or a system, and A refers to the acceleration of the system as a whole. That means this can be a simple body, and this is a whole system. You have a train, you have all those things which are happening here. So any internal force is not included. Please understand, no internal forces are included. The second law of motion is local relation, which means that force at any point is local. at some instant, which is related to the acceleration at that instant only, not by the history of motion. That is, if you throw a stone out of this running, say, moving cart or train, then once it is out of this system, and you can say out of this train, the force and acceleration will not depend on this anymore. So it will be local. Here only we'll find out. The bullet of mass 0.04 kg moving with a speed of 90 meter per second enters a heavy wooden block and is stopped after a distance of 60 centimeter. What is the average resistive force exerted by the block on the bullet? So the retardation acceleration, we know that you can use easily v square equal to u square plus 2as here. Acceleration, because retardation is there, so it will come in negative. The distance is also given 60, so we have to divide it by 100, so we get 0.6. And mass is also there, but the initial velocity is 90, the final velocity will be 0. So when we put all these values here, acceleration is this much, minus 6750 meter per second square. And then you can easily find out the force, because the question is about force. Now this is the acceleration and the mass is 0.04. So mass into acceleration is the F, right? Force. So this is the resistive force, and basically it's a retardation. The bullet is coming, so it has to stop. This is the question is all about. The motion of a particle of mass m is described like this. Find the force acting on the particle. So we have y equal to ut plus half gt square. Let us take the differential. So this dy by dt will be equal to d derivative of ut and half gt square. So we'll derivate in terms of t. So v will be dy by dt. This t will go. This t square will become 2t. So this will be v. Again, let us differentiate it again, because acceleration is dv by dt. So let us take a derivative of this one. This will go. This g will remain like this and t will go. So acceleration is actually equal to gravity. So what will be force? Force is mass into acceleration. And in this case, a becomes equal to g. So this will be g. F equal to ma or mg. This is the, and this equation describes the motion of a particle under the action of or acceleration of gravity. Impulse. When you are hitting a cricket ball, or say hitting a football which is moving, so the change in momentum, or you can say the force, is acting for very short duration, which is changing the momentum of the body, velocity of the body, because mass remains constant. The scenario here is that for a very small duration, a heavy force is applied. So we come to another variable or property in motion, which is the product of force into time. Force applied for certain time, and this time is very less, and which is causing the change in the momentum, because velocity is being changed, so momentum is being changed, and this is the measurable quantity, and this we call it as impulse. So impulse will be simply force into time, which is equal to the change in momentum, which is causing the change in momentum, and which is we can say a large force acting for a very short span of time. It produces a finite change in momentum, and this is called as impulsive force. This impulsive force, and traditionally they were put in ordinary forces, but as we know, Newtonian mechanics, they have no such distinction. Impulsive force are like any other force. The only thing is they are very large and they act for a very short time. Let us take an example. A batsman hits back a ball straight in the direction of the bowler without changing the initial speed, that it remains 12. If the mass of the body is 0.15 kg, we have to determine the impulse imparted to the ball. Now the initial momentum was m1 v1. The final is m2 v2. We know that the mass remains the same, so it will be simply, let us take mass here, mv1 minus v2. Okay, so mass is, we are finding the change in momentum. So this mass is 0.15, 12, ball is coming this side, now ball is going this side. So one will be 12, other will be minus 12. So 12 minus of minus 12, that is 12 plus 12, and that is multiplied by 0.15. So 24 into 0.15, this will give you 3.6 Newton second in the direction from the batsman, because batsman has hit this ball in the direction of the bowler.
Newton's third law of motion. What did the second law says? It says force is directly proportional to acceleration and mass. Okay. So the external force on the body causes certain acceleration. From where does this external force act? What is the origin of this external force? What is the agency which is providing this external force? When we talk about Newtonian mechanics, the external force is arising due to some other system or body. If you consider two bodies, say A and B, then B gives rise to external force on A. Now the question arises, does A in turn give rise to an external force on B? That is, if this is A, this is B. If A is giving some force or thrust to B, what is B giving to A? If you press a coiled spring, the spring is compressed by the force of your hand. The compressed spring in turn exerts some force on your hand and you can feel it easily. But what when they are not in contact? Bodies are not in contact. For example, earth, it pulls anything downward due to gravity. Now what is stone doing with earth? Means if this is earth, there is a stone or any other body. Now earth has a tendency to bring the item back, body back, because there is a gravity, center of the earth has some gravitational pull. Now when it falls or when it is falling, does this stone also provide or gives some or resultant force on this earth? The answer is yes. And what is that force? We can't feel it. The mass of this body is very less. This stone is negligible as compared to the mass of earth, so we don't feel it. According to Newtonian mechanics, force never occurs singly in nature. These are two bodies, so the force is the mutual interaction between these two bodies. In other words, we can say that force always occur in pairs, and the mutual forces between two bodies, they are always equal and opposite, and this idea is expressed by Newton in the form of third law of motion, that says to every action there will be always an equal and opposite reaction. So this is quite crisp. This line is very crisp, very beautiful also, and in common language we can say like this. But because of this simple line, there may be some misconceptions. We need to point out certain important facts about the third law. What is action, what is reaction especially? So the term action and reaction in the third law means nothing else but the force. Action reaction means force. we can use different concept, but that will be confusing, so we'll stick to the force. A better way to state the third law will be force always occur in pairs. So force on body A by body B is equal and opposite to the force on body B by body A. The action and reaction pair in third law, they may give some wrong impression that action comes before reaction. Action is the cause. Action is the cause and reaction would be the effect. So there is no cause-effect relationship implied by the third law. And the force by A on B or A by B and the force on B by A, they would act at the same instant. In the same reasoning, any one of them can be called action and reaction. So action and the reaction forces, that is FAB, force on A by B, and they act on different bodies, not on the same body. So these are two pairs, A and B. So this is A by B, force on A by B, and this is force on B by A. So if we are considering the motion of any object, say A or B, only one of these two forces may be relevant. It would be an error to add up these two forces, and we can not claim that the addition of these two is zero. But when you are talking about a system as a whole, means this is for this scenario, it is not acceptable. But when we are considering a system that is two bodies as a whole, that is FAB and FBA are the internal force which are acting on a system A plus B, both the bodies are involved, means you consider them as a system. Now they add up to give a null force, and internal forces in a body of a system of particle, they will cancel away in pairs, and this will be very important. We'll see in next discussion also and solving the questions also. Let us take an example. Two identical billiard balls strike a rigid wall with the same speed but different angles, one like this and one with certain angle. What is the direction of the force on the wall due to each ball? What will be the force? And the ratio of the magnitude of impulses imparted to the balls by the wall. So what will be the force imparted or applied in result to the ball striking it? And we'll use see, the very intuitive answer will be, might be the force on the wall will be normal to the wall like this, and in this case it is inclined at say 30 degree. This is 30 degree, but this intuition may be wrong. The forces on the wall is normal to the wall in both the cases, so they will be normal, means perpendicular, this perpendicular, this perpendicular, so they will be in both the cases they will be normal to the wall. So how we are going to find out the force on the wall? There is a trick. We'll consider the force or the impulse on the ball due to the wall using the second law, and then we'll use the third law. Means let us say that u is the speed of each ball before and after collision, because the speed is not changing, and m is the mass of the ball. Say m is the mass of each ball. Now we will consider axis as given in this figure, and also consider the change in momentum of each ball. In this case, first, if this is u, this is m, initial momentum is m into u, then this strikes the wall and comes back, returns back. So the velocity first it was in this direction, then it will be in opposite direction. So the px in this case will be this direction, py is 0 because this is normal to the wall. So mu and then return minus mu. So this is px initial, px final, and the py in both the case will be 0 because this is normal, perpendicular to, if you can find it, the cos theta, u cos theta, u sin theta, you will find out that ultimately the y component is going to be 0 because of the cos component or the theta component. Now impulse is what? It is the change in the momentum vector. So mu, this is the resultant, minus mu minus of mu, that is minus of mu minus mu, and that will give you minus 2 mu, and if you add these two, that will be 0. So y component will be 0, and in this case the impulse and force are in the same direction. The force on the ball due to the wall is normal to the wall because it is not going anywhere, and this will be along this negative x direction. As you see here, the sign is also showing that. And if you use the Newton's third law of motion, the force on the wall due to the ball is normal to the wall, that is in the positive x direction, right? The magnitude of force we cannot ascertain since the small time is taken for the collision, and which is not specified in the problem, so we'll leave it at that. Now let us come to the second part. It is striking and coming back like this. So this is the direction and this is the direction. So what will be the px initial? That will be mu cos theta. See, if I make this as cos theta and this as sin theta, this is theta, the direction is like this. So what will be the px? Always, if you have any direction like this, x component is this and y component is this. In this case we have x component and this is what the y component. So x component will be mu cos theta and y component will be minus mu sin theta, right? In this case px final, it is going like this. So what will be the x component, which will be again, because in this case if this you take cos theta in this direction as plus, in this case you have to take it as negative, right? Because in this case the cos is like this, in this case the cos is like this, so it will be minus mu cos theta, but the y component remains the same for both of these, okay? So it will be minus mu sin theta and this will be minus mu sin theta. Now this px, the x component is changing sign after collision. See, mu sin theta and this is minus mu sin theta, while this is not changing. Now what will be the x component of impulse? Mu cos theta minus of mu cos theta, that is minus 2 mu cos theta, and when you add these two, means minus mu sin theta, not add, we have to subtract, minus mu sin theta minus of minus mu sin theta, that will be plus mu sin theta, these two cancels out and y component will be 0. So the direction of impulse in this case is as we saw, it will be the normal to the wall along the negative x direction, and using the Newton's third law we'll find out the force due to the ball, which is normal to the wall along positive x direction, and the ratio of magnitudes will be, previously what it came, it was this value, then we got this value, divide 2 mu by, rather minus sign will be cancelled, so 2 mu by 2 mu cos 30 degree, which will be 2 by root 3, which comes to 1.2. Conservation of momentum. There is an important result or consequence of the second and third law. This is the law of conservation of momentum. Just consider a bullet being fired from a gun. So if the force on the bullet by the gun is F, the force on the gun by the bullet will be what? It is a recoil. It will be minus F. Bullet will, see, if the bullet goes like this, there will be a recoil in the opposite direction. So if this is F, this would be minus F, according to the third law of motion. And the two forces are acting on common interval of time, that is delta t, same. So what is the second law, which is F? This delta t is the change in the momentum of the bullet, F delta t for this one, same time, and minus F delta t is the change in the momentum of the gun. And since both are at the rest, the change in the momentum equal to the final momentum for each. If Pb is the momentum of the bullet after firing and Pg is the recoil momentum of the gun, that is mass into velocity, that is F into delta t also. So Pg will be equal to minus Pb by this discussion, they are opposite. Take this on the left hand side, Pb plus Pg will be 0. So total momentum of that is bullet plus gun will be conserved. So when we say an isolated system, that is the system which has zero or no external force, the mutual forces between pairs of particles in the system, this can cause momentum change in the individual particles. But since the mutual forces of each pair are equal and opposite, the momentum changes cancel in pair. That is why the total momentum remains unchanged. And this is the law of conservation of momentum. So the total momentum of an isolated system of interacting particles is conserved. Let us take an example. Collision of two bodies. When two bodies are colliding like this is coming from this side, this is coming from this side, and they get apart now. They are initially like this, then they collide, and this is in this direction, then it goes in another directions. So if we have A and B, these two bodies are there. The initial momentum, which is PA and PB, so PA here, PB here, and the final momentum, say it will be PA dash and PB dash. And by the second law, we know that F A on B into delta T, which is nothing but the impulse, is the change in momentum. So PA dash minus PA. Again, B on A will be P dash B minus PB. Same interval has been taken because they collide for same interval. Now we know by third law, FAB will be equal to minus FBA. That is, the forces will be equal and opposite for both. In FAB, put this, and FBA, put this. Now rearrange, that is, take PA dash and P dash B here, means you have to take this on the left hand side, this on the right hand side. So P dash A plus P dash B equal to PA plus PB. What this is showing is the total momentum, final momentum of the isolated system is equal to the initial momentum. And this is even true for elastic as well as inelastic collision. So in elastic collision, there is a second condition, that the total kinetic energy that we'll talk about of the system will be equal to the total final kinetic energy that we are going to see in the later discussions. So there is equilibrium of particle, that is when no net external force, that is zero net external force is acting, this points to equilibrium of a particle. We have first law. This means that the particle will either be at rest or in uniform motion. So if two forces F1 and F2, they are acting on a particle, F1 will be equal to minus F2. That means that two forces on the particle must be equal and opposite, which is our one more law. Even if you have more forces, that is F1, F2, F3, these are concurrent forces, the vector sum of these three forces is 0. So F1 plus F2 plus F3 is equal to 0. So if this is F1, this is F2, they are equal and opposite. If you take three forces, say F1, F2, F3, then F3 will be, if we can just rearrange this, F1 and F2, this will be F3. So what we are saying here is the resultant of any two forces, say F1 and F2, which is obtained by, of course, the parallelogram law, must be equal and opposite to F3. So we have three forces, and you see we have taken a triangle, the vector arrows, these are making some, the sense of where it is acting, and the result can be generalized to any number of forces. You can take from Fn to F1 to Fn, and can be any number of forces. And because there are three forces, we have a triangle. You can take n-side polygon for Fn. Also, the x component, the y component, the z component has to be 0 like this. A mass of 6 kg is suspended by a rope of length 2 meters from the ceiling. So this is from here to here, it is 1 meter, from here to here it is 1 meter. So in all it is 2 meters. A force of 50 Newton in the horizontal direction, this is force in horizontal direction is applied at the midpoint of the rope. So what is the angle of the rope, or this angle the rope makes with the vertical in equilibrium? So this angle we have to find out. We have to neglect the mass of the rope. In this case, we make free body diagram. So what are the free body diagram? There are two things which are happening here. For this body, okay, what is happening, and at this point what is happening. So these are 2 points which we need to concern or consider. First, let us make the free body of this part. So we have this weight 60 Newton is down, means acting downwards, and tension T2 is acting upwards. In this case we have 50 Newton as said in the question. Of course it has T2 also, so T2 will be like this, and there is T1, so this will be T1. So this is 50, T2, T1. Let us take for this one. So T2 will be equivalent to 60 Newton by the equilibrium of the weight. So T2 is simply 6 into 10. 10 is gravity. So it will be, tension will be, T2 will be 60 Newton. Let us consider this equilibrium of point P under the action of 3 forces. So there are 3 forces, T1, T2 and 50. The horizontal and vertical component of the resultant force, because this is at rest, so it has to vanish separately. So T1, this component will be T1 cos theta, and this component will be T1 sin theta. So T1 sin theta will be equal to 50, and T1 cos theta will be equal to T2. So what we have done here, T2 we have just found out it is 60 Newton, so just place it here. T1 is 50 Newton, it is given in the question. Let us divide these two. Tan theta will be 5 by 6, theta will be tan inverse of 5 by 6, so this angle will be 40 degree. Common forces in mechanics. So there are certain forces which are talked about, but the gravitational force or the magnetic force, these are also certain force which come into picture. So there are certain forces which are contact forces, there are certain forces which are not contact forces. That means the gravitational force is not a contact force. But when you are talking about a book resting on a table, or say a system of rigid bodies connected by rod, hinges and other supports, there are contact forces. And the component of contact force normal to the surface is called normal reaction. So any body which is placed, say a book is placed here, so if this is mg, there will be a contact force. You can also say that in water also, fluid also, you will find it. If you press something inside this water, say a cork, there will be an equal and opposite forces of force, resultant force, and that is the buoyant force. The upward force applied by the liquid or fluid is the buoyant force. The air resistance, viscous force, they are also the contact forces. And two other common forces, as you see here, is the tension in the string, the force due to this spring, and of course this is given by F equal to minus kx by, if we have this mg, say some force, this is some kx, and kx is x is the displacement of this spring, so compression is also a part being played. And these are all the type of different forces which may act. As I said, gravitational force and electrical force, these are also relevant to the mechanics part. But you will be surprised when we are talking about uncharged and non-magnetic bodies in mechanics. In this case, see, the different forces, when we are talking about electric forces, they come from some charging and uncharging. So we will try to talk about the macroscopic scale, not to the internal level like electrons, etc., nuclei and electrons. Friction. What is friction? That is how we walk. So the force of gravity, as we saw, that something is placed on the table, the force of the gravity we have, and why this body is at rest, why it is not moving, there is some force, something which is holding this body. Of course, the gravity is there, there is a force also, but when you push it, very mild force, if you apply, then you see that it is not going to move. Why it is not moving with mild force? You are applying some force, it is mild force, but the net force is 0. But when you apply certain more force, this is going to move. So when a body is at rest and there is a force applied and this is not moving, this force, which is say impending force, or the force which is stopping this to move, not allowing it to move, this is called Fs, or static force. But when you press with some more energy, this is going to move. So the force which is now impending or trying to resist this your energy or this movement of this body is Fk. S is for static, and this F sub k and F sub k. So this S and K stands for static and kinetic. So static and sliding forces you are seeing here. Fs is parallel to the surface of the body in contact with the table. This is frictional force, or you can simply call it as a friction. And there is a subscript, as I said, that when it is moving, it will be Fk. So these are the impending motion of the body in this case, which is opposed by the static friction. And when the external force exceeds the maximum limit of static friction, the body begins to move. And once the body is in motion, it is subjected to sliding or kinetic friction, which is Fk, which is again opposing the movement. And this kinetic friction Fk is generally less than Fs. As you see here, Fs, you are applying force, but it is not moving, very little force. When you are applying more force, it has started moving. Now the Fk becomes less than Fs generally. And when there is no force applied, as I said, there is no friction, means no static friction. It comes into play when you actually apply a force. So this Fs is what it is opposing. So that is why we are calling it as a static friction. The body is kept at rest. This is the impending motion. This Fs max is at what point you actually push it and it starts moving. So Fs max is that static friction max, and this force is the maximum force that can hold that body, beyond which if you apply the opposite force, the body is going to move. So Fs max is first of all, it is independent of the area of the contact, but it varies with the normal force. So this is directly proportional to the n, that is the normal force. So we have this mu s. You can say this Fs is directly proportional to n. So this proportionality sign can be changed to mu s. This is the constant of proportionality, and we call this mu s is the coefficient of static friction. And the law of static friction, this can easily be written as Fs, because this is about maximum. When you talk about normal Fs, that is F sub s, that is static friction, it is less than or equal to mu s n. When it becomes equal, that means you are trying to judge the maximum static force. So if the force you apply, or the applied force, exceed this Fs max, the body is going to slide. It starts moving, below which it is not going to move. And the friction force that is opposing the motion is called the kinetic or sliding friction, which is known as, which we represent by Fk. And again, the kinetic friction is also independent of the area of the contact, and nearly they are independent of the velocity also. Now what Fk has, Fk is similar to the Fs, so it is also directly proportional to the normal force. So we have this mu k as the proportionality constant, and this is known as the coefficient of kinetic friction. So if we apply, say, some F force, let us see here. If we apply some F force, this is Fk acting on the other side. So F minus Fk will be equal to what? Ma. The resultant force will be equal to mass into acceleration. So acceleration will be F minus Fk by m, which is given by this. And if we have a constant velocity, this acceleration will be 0, this whole will be 0, so F minus Fk will be eventually be 0, so F will be equal to Fk. Okay. And if the applied force on the body is removed, the acceleration is minus Fk by m, because the body is going to eventually stop. So the laws of friction which we just saw, they do not have this one and this one, they do not have any they are not fundamental laws like those for gravitational and electrical and magnetic forces. They are just empirical relation that we will be using to solve our problems. So when two bodies are in contact, each experiences a contact force by other, and friction, as we said, by definition the component of the contact force which is parallel to the surface. Again, if this body is kept or some car is moving, some sort of body is there, so this contact, this is the friction which is acting on it. This is a relative motion basically, because the frictional forces is opposing. Okay, if a box is lying in the compartment of a train which is accelerating, we have friction. So all these are in the examples, these are all the examples of Fs and Fk. Let us take an example, you will understand it better. Determine the maximum acceleration of train in which a box lying on its floor will remain stationary, given that the coefficient of static friction between the box and the train floor is 0.15. In this case, the acceleration of the box is due to the static friction. Okay, so force is what? M into A. So what this will be? We know that Fs is less than equal to mu s n. This already we know, this expression. N is what? This is normal force. So if this is the normal force, what will be there? That will be equal to mg. Let us put mg in this case. So ma will be equal to mu s into mg. Gets cancelled out. A will be equal to, or A will less than equal to mu s into g. Mu s is also given, g is also given. Just multiply them. This will be 1.5 meter per second square. In this figure, a mass of 4 kg rests on a horizontal plane. So it is resting, it is not moving. The plane is gradually inclined until at an angle 15 degree. With the horizontal, the mass just begin to slide. So initially it was like this, then it was taken up this one. So it goes like this. When it reaches this 15 degree, the mass would slide. What is the coefficient of static friction between the block and the surface? So we have certain component we have to make here. The forces acting on a block of a mass m at rest on an inclined plane are what? First of all, we have this weight mg. There is a normal force. Normal force always act normal to the surface. So if this is a surface, this will be the normal force. Okay. Then we have this Fs. This is also acting, which is the impending force, static friction force. So because it is at equilibrium, the resultant force or the resultant of these force must be 0. So if this is mg, if this is theta, this will also be theta, by trigonometry. If this is mg, this will be mg cos theta component, this will be mg sin theta component. So if these are all in equilibrium, so Fs has to be equal to mg sin theta and has to be equal to mg cos theta, which is done here. But as we increase the theta, this self-adjusting frictional force Fs increases until theta is equal to theta max. And theta max is what? It is given that theta max, the maximum angle is 15 degree. So this Fs max is, we know that Fs max is mu s into n. This tan theta max is equal to mu. We just have to divide these two, this one and this one. And theta max will be tan inverse mu s. Okay. When theta becomes just more than this theta becomes more than just more than theta max, there will be a small net force on the block, and this is going to slide. And theta max depend only on this mu s, and it is independent of the mass. So what will be the theta max? It is given as 15 degree. So you can always find mu s by putting 15 degree here. This is equal to 0.27. What is the acceleration of a block and the trolley system shown in this figure? If the coefficient of kinetic friction Fk between the trolley and the surface is 0.04, and what is the tension in this string? We have to take G equal to 10 meter per second square. So this is the whole scenario. You have a trolley system. This is a block, and we have a trolley system here. This is a trolley. So we have, when it is moving, we have Fk as the opposing force, that is the surface force, because it is moving, so we have Fk. This is 20 kg. This is tension, and the same tension will be here because this is a pulley. 30 Newton or 30 Newton will be the force, that is because of gravity. So let us make the free body diagram of these 2 points. First we'll make this one. So we have a tension here, so T tension is given like this, and of course 30 Newton is acting downwards. So T minus 30 is the actual force, which will give you mass into acceleration. Mass is 3 kg. So 30 minus T equal to 3 into A. In this case, we have tension here, which is this one. Fk is opposing, and this is 20 kg. So this T minus Fk will be equal to m into A. Mass in this case is 20 kg. So T minus Fk will be 20A. And we know for this Fk, what will be the Fk? Fk will be equal to mu k into n. This we already know. Mu k is given as 0.04. Put it here. So n will be simply 20 into 10. That is 200 Newton. Now put these value Fk we have found out in this, and this gives you another scenario. We have to just solve these 2 equations. We get acceleration and T. What is the rolling friction? A body, see, if you have a ring or a sphere, if you just roll them, they goes for long, means they travel for long, or they are in motion for a considerable amount of time. In case you just press or give motion to this body, it is going to just stop here, but the sphere or a ring is going to go long. Why this scenario is? Because the friction force which is acting here is less. The actual area which is touching the surface is less because it is moving. But in this case, it is long. And as we said, the friction is independent of the area, but because the surface which is in contact is very less. I hope you got the idea. So that is why because these friction forces, movement friction forces, they are very difficult to handle. Means the machines which are acting, these motors are actually acting against the friction forces only. But there are certain ways in which we can solve it. We can put, these are the ways of reducing friction. We can add the ball bearing, which is placed between moving parts of a machine. We can have some compressed cushion of air between surfaces, which gives rise to, or we can minimize this friction. Circular motion. Circular motion, the acceleration of a body which is moving in a circle of radius r with uniform speed. We have already known that if it is v, then the acceleration is given by v square by r. V is the velocity, r is the radius, and this is towards the center. And according to the second law, we know that F equal to m into a. If this is the acceleration v square by r, this F becomes mv square by r, where m is the mass of the body. Now this force is directed towards the center. This is called the centripetal force. What it is called? It is called as centripetal force. If you rotate a stone in a circle by a string, the central or the centripetal force is provided by whom? Of course, the tension in the string. So this CP or centripetal force for motion of a planet around the sun is the gravitational force on the planet due to the sun's gravity. If we have a car, say this one, say it is taking a circular turn on a horizontal road, the centripetal force is the force of friction. So there are plenty of forces which gives rise to centripetal force, like the force of friction, like the gravitational force, like the tension in the string. A circular motion of a car on a flat like this and on a banked road gives us various interesting application of the laws of motion. Let us start with the motion of a car on a level road. So this is a level road. So what are all the forces which are acting? This is mg, this is the weight, this is of course the normal reaction N, and this is the frictional force. So as there is no acceleration in the vertical direction, means it is not moving up or down, so this N will be equal to mg, that is N minus mg will be equal to 0. The centripetal force which is required, as we said, that this is by a force of friction, so it will be along the surface of the road, and this is provided by the component of contact force between the road and the car tires. Means this, here the force is going to work, this is the force, and by definition we know this is a frictional force, and it is a static friction that is providing the centripetal acceleration. Please understand that the static friction is providing the centripetal acceleration. And what this static friction is doing, it is opposing the impending motion of the car, which is moving away from the circle. And as we know that F is always, this Fs is always less than equal to mu s n, and this force can be written as mv square by r. Let us compare them or equate them. Then v square has to be less than equal to mu s r into n by m, and we can take this this q, or say n is equal to mg. We know that n is like this, mg is like this. We can take this n equal to mg, and this equation forms like mu s into r into g. And see, there is no m, there is no mass here, so it is independent of the mass of the car. So what it shows is, for the given value of mu s, that is the coefficient of static friction, and the radius, there is a maximum speed of circular motion of the car. Let us take this v square here under root, so this becomes mu s rg under root, mu sub s. Now when the car is moving on a banked road, we need to take some certain contributions, that is the x and y contributions. So if this is a car on a banked road, of course mg will be down below, and normal will be this. If this is a surface, normal is always normal to the surface. So this, if this is theta, then this is the cos component, n cos theta, and this will be the sine component. Okay, one will be sine component, one will be the, for n, we are talking about n cos theta, and this will be n sine theta. For F, this is the frictional force, so this will be the sine theta, and this will be the cos theta. So this is going to add up, and if it is at rest right now, or if there is, since there is no acceleration along the vertical direction, the net force along this direction must be 0. That means this n cos theta has to be equal to mg plus f sin theta. This should be equal to this, right? See, this is the simplified diagram, or you can say free body diagram. This is n cos theta, n sin theta, f, this is f, so f sin theta, f cos theta. So f cos theta plus n sin theta will be providing the centripetal force. So f cos theta plus n sin theta, f cos theta plus n sin theta will be giving mv square by r. And how about this? N cos theta will be equal to f sin theta plus mg. So these are the two equations. But we know that the static force should be less than equal to, or it is less than equal to mu s n. So how to obtain this V max, velocity max, when force is this static force is actually equal to mu s into n. Now when we use this and this, we get n cos theta is equal to mg plus this. For f we replace mu s n, so mu s n into sin theta. Again, another equation we can put mu s n in place of f, and when we solve these two equations, we get n equal to mg by cos theta minus mu s sin theta. We can substitute n also in this one. We get another equation. We can just rearrange so that we can find out this v max. This is rg mu s plus tan theta by 1 minus mu s tan theta under root. And when we compare this with the previous equation of the maximum possible speed of a car on a banked road, this is greater than that on a flat road. Okay. In case this static friction is 0, this v0 becomes rg tan theta, and this is under root. So at this speed, the friction force is not needed to provide the centripetal force, because driving at this speed on a banked road will cause very little wear and tear to the tires. And this equation also tells us that this v is less than v0. That is, frictional force will be up the slope, and that a car can be parked only if this tan theta is less than or equal to mu s. Let us take an example so that we understand better what we learned here. A cyclist speeding at 18 km per hour on a level road takes a sharp circular turn of radius 3 meter without reducing the speed. The coefficient of static friction between tires and road is 0.1. Will the cyclist slip while taking the turn? So we have a certain scenario. If the road is unbanked, the frictional force is going to provide the centripetal force needed to keep the cyclist moving in a circular turn without slipping. But if the speed goes very large, or the turn is very sharp, that is, it is very small radius, or both of the condition, the friction force is not sufficient to provide the required centripetal force, and the cyclist is likely to slip. So the condition for the cyclist not to slip is simply v square should be less than or equal to mu s into rg. And all the values are given, so let us put this r as 3 meter, g as 9.8, mu s as 0.1. So this gives you 2.94 meters square per second square, meter per second square, whole square. Now velocity is given as 18 km an hour, just multiplied by 5 by 18 so that we can get it in meter per second. So this v becomes 5, so v square will be 25. And we see that this value is 25 and this whole value is 2.94. So the condition is not obeyed. The cyclist will fall, will slip while taking the circular turn. A circular racetrack of radius 300 meter is banked at angle 15 degree. If the coefficient of friction between the wheels of a race car and road is 0.2, what is the optimum speed of the race car to avoid wear and tear on these tires, and maximum permissible speed to avoid slipping? So this is on the banked road, right? So we have just learned that what should be the required equations. So on a banked road, the horizontal component of the normal force, that is this one, and this normal force. So horizontal component, if this is n cos theta, and this is fs. So this is fs, or friction force. So again, this is the cos theta for this fs or f. So the cos component of n and the cos component of the friction force, they are going to provide the centripetal force. Without slipping, it should run. At the optimum speed, the normal reaction component is enough to provide the needed centripetal force, and the frictional force is not needed. So the option speed or optimum speed v0, we know that it is equation we just learned. v0 is given by under root of r into g into tan theta. R is 300 meter given, theta is 15 degree, and gravity is 9.8. Let us put this value here. You get v0 equal to 28.1 meter per second. So what will be the maximum possible speed, Vmax? This is given by this equation. Put all these values, r, g, mu, s and tan theta, because everything is given here. You get 38.1 meter per second. How to solve problems in mechanics? First of all, 3 laws of Newton, and there are various other variety in which not only single force may be acting. There may be different forces acting say gravity, some push, some pull. So there is a whole assembly of the part. So how to really take some into account and some not into account? So if we want to handle a typical problem in mechanics, then we need to understand certain steps. First of all, we need to draw a diagram which shows schematically the different parts, various parts of assemblies of bodies, like the links and the supports, etc. For the option of choosing a convenient part of the assembly, as one system has to be there, a free diagram, a free body diagram, we need to draw a separate diagram which shows this system and all the forces on the system by remaining part of the assembly. We need to include the forces on the system by other agency and do not include the forces on the environment by the system, okay? And we call it as a free body diagram. So in a free body diagram, this will include the forces, their magnitudes, the directions, and the direction of the tension, like in a string, should be along its length because we are sure about it. And if you are not aware of something, then let it be unknown, because we'll be applying the laws of motion to compute it. If it becomes necessary, then we can follow the same procedure for another choice of the system. And then you can employ the Newton third law. Every action has equal and opposite reaction. If in a free body diagram, say A, the force on A due to B is F, then in the free body diagram of B, the force on B due to A should be minus F. Let us take an example so that we understand what we have learned. A wooden block of mass 2 kg, it rests on a soft horizontal floor. When an iron cylinder of mass 25 kg is placed on the top of the block, the floor yields steadily, and the block and the cylinder together go down with an acceleration of 0.1 meter per second square. What is the action of the block on the floor before and after the floor yields? Gravity has to be taken this one and identify the action-reaction pair in the problem. First, you see the diagram. This is a block, okay, and this is the free body diagram of this block. We have mg here and reaction force here. When we put a cylinder, this goes down, this goes down. So there is an acceleration, 0.1 meter per second square. So the free body diagram of the whole system, free body diagram for this block as well as the cylinder system, is like this. This r dash is equal to 270 n. So what is happening is the block is at rest. So it's free body diagram. We'll just know the force of gravitation, which is acting like this. So it will be 2 is the weight and 10 is the gravity. So it will be 20 Newton. And the normal force, this R, is by the floor on the block. So by the first law, the net force on the block must be 0 because it is rest. So R is 20 Newton. And we apply the third law, the action of the block is equal to the reaction, 20 Newton, and directed vertically upwards. So this is 20 Newton, R is equal to 20 Newton. When we come to this one, means the system, which is block plus the cylinder, the acceleration is given. So the free body diagram is given like this, and the force of gravity due to earth is 270 Newton and the normal force R dash by the floor. So this R dash, or you can say this is higher, so 270 minus R dash will be equal to m into a. Means whole acceleration force equal to ma, force, resultant force is 270 minus R dash. So 270 minus R dash is equal to 27 into 0.1 Newton. This is the whole weight. What is the complete weight? This plus this. And 0.1 is the acceleration. So what will be R dash? This will be 267.3. So all this action-reaction pair we have to consider the force of gravity in this case. This is 20 Newton on the block by the earth, and the force of gravity on the earth by the block, that is a reaction, is equal to 20 Newton, again directed upwards. The force on the floor by the block, this is action, and the force on the block by the floor is the reaction. In this way, we can know about the other stuff also. Let us summarize what we have learned. Aristotle, he gave the first view, and he said that in order to move a body in uniform motion, there has to be certain force. But eventually, it came as not the correct observation, you can say, and this was proven wrong. That is, a force is necessary in practice to counter the opposing force of friction. This is the truth. So Galileo, he extrapolated the simple observation he saw of the motion of body on inclined plane like this, moving like this, or in which the law of inertia he inserted. So Newton first law of motion is the same law rephrased from Galileo. Everybody continues to be in a state of rest or uniform motion in a straight line unless compelled by some external force to act otherwise. Or you can say, if external force on a body is zero, that is, acceleration will be zero. The momentum of a body is simply product of mass into velocity. Newton's second law of motion says the rate of change of momentum, that is dp by dt, is proportional to the applied force. So F is, you can say F is directly proportional to rate of change of momentum and takes place in the direction of or in which the force is acting. So this is just the K, which is the constant of proportionality. You can take K as 1, and the force becomes dp by dt, and this dp by dt is simply dp is mv, mass into velocity, so dmv by dt. So m we can take just outside. This is dv by dt, and dv by dt is nothing but a. So this becomes m into a, and this is the main law. The SI unit of force is Newton. 1 Newton is simply 1 kg meter per second square. The second law is consistent with the first law. If acceleration is 0, force is 0. It is a vector equation, and it is applicable to a particle, to a body, or a system of particles, provided this F is the total external force. F has to be external force on the system, and this acceleration of the system should be, this total external force is creating some certain acceleration. F at any point at a certain instant determines the acceleration at same point at that instance. That is, the second law is local, very local. If you throw a stone out of a train or a car, then the stone, when it is coming out, then it will not be related to either train or car movement. So A at an instance does not depend on the history of the motion. Now impulse is simply force into time. So this is the product of force and time, which is actually equal to the change in momentum. And the notion of this impulse is very useful when a large force is acting for a short time to produce a measurable change in the momentum. And since the time of action of force is very short, very, very short, we can assume that there is no appreciable change in the position of the body during the action of impulsive force. What is the Newton third law of motion? To every action, there is equal and opposite reaction. What we can say here is, if we have A and B, a force in nature, they always occur in pairs of bodies. So force on A by body B is equal and opposite to the force on body B by A. So action and reaction forces are simultaneous forces. There is no cause-effect relation between action and reaction. Any of the two mutual forces can be called, it can be called as action, this can be called as reaction. The internal action and reaction forces between different parts of the body, they sum up to 0. Then we have law of conservation of momentum. The total momentum of an isolated system of particle is conserved. Okay, the initial has to be equal to final momentum. So this law follows from the second and third law of motion. Friction. Friction is the force. So frictional force which are opposing or which opposes impending or actual relative motion between two surfaces in contact. So this is the action of frictional force. It is the component of the contact forces along the common tangent to the surface in contact. So if you have a block here, so this is the surface. So here the force is acting. The static force Fs, F sub s, opposes impending relative motion. So it does, when a body is at rest, the force acting is Fs. When the body is moving, the friction force becomes kinetic friction, F sub k, and this opposes actual relative motion. They are not dependent on the area of the contact, and they satisfy certain laws. These are approximate law. These are not the actual laws. So this static friction is less than equal to mu s r. If this Fs is max, means after the body will start moving, this has to be equal to mu s into r. When we talk about Fk, F sub k, kinetic friction, this is mu k into r. This mu s is the coefficient of static friction, mu k is the coefficient of kinetic friction. These are constants, characteristics of the pair of surface in contact. It is found that this mu k is less than this mu s. So consequently, this Fk is less than equal to this Fs. These are certain quantity, symbol, units, dimensions and remarks. Momentum P is given by m into v. So it is a vector. The unit is kg meter per second, mlt minus 1. Force is mass into acceleration. So Newton is the unit, mlt minus 2. This is the second law. Impulse is force into time, which is actually equal to change in momentum. This is given in kg meter per second or Newton second. It is mlt minus 1. Static friction and kinetic friction, Fs and Fk, both are Newton, both are mlt minus 2. And Fs is less than equal to mu Sn. And for Fs max, it has to be equal to mu s into n. Fk is equal to mu k into n.